Okay, so I was going to say doing steepest descent last time, it's constant gradient time, but not quite yet. Constant gradient method is a very difficult method to derive, and it's using sensible derivation we go through other methods first. So we have one more intermediary, and a bigger problem is I have no decent chalk here. So I guess it's, what?
Uh-oh.
Yeah, well, I have plenty.
Come back next week. Are you gonna go home? Church. Are you hungry for eggs? Yes, you are. Then next week. Yeah.
Now, let's see. Well, feels like it's been quite a while. It's only been since last Thursday, but anyway. So, we're solving a symmetric positive definite system. Presented the method of steepest descent. That would recast x equals b as a problem minimizing the function. And so we take at each iteration the direction of steepest descent from where we were to try to make that function's value smaller and smaller. And can anyone tell me what was bad about steepest descent? Like in the one of the examples I showed you. Yeah. Yeah, and how did the search directions behave as the process unfolded?
There's one zigzag.
Yeah, it was a zigzag. Yeah, each one was perpendicular to or orthogonal to the previous one, but then the one after that, there was no independence whatsoever. It would just retrace all steps. So we want to give steepest descent some memory, and I gave you indications how we're going to do that. Each search direction was not going to be just the steepest descent direction, but we're going to add a little something to it. But I want to really flesh out how that comes about. So the goal, so we're solving A equals B, A is SPD, and eventually today I will get to constant gradient method, but like I said, we have to go through another method first. So the goal is to make all search directions at least linearly independent. If they can be made orthogonal, that would be even better. It turns out we're not going to be able to do that exactly, but in some sense we will be able to. So you could think of it as steepest descent with memory. So it actually keeps track in a way of what directions you've used before. We'll not use them again. Okay. So the way that we can enforce that is first thing I'm going to do is prescribe that each iterate, we'll call xk, is a linear combination of vectors that are orthonormal vectors. So each of them is going to have this form, a matrix QK, which is n by k, and then yk is a vector, there's a k by 1. And QK has orthonormal columns. So it kind of satisfies that relationship. Okay. So the idea is QK is a linear combination of these vectors, and then as we go from each iteration to the next, we come up with a new vector, like QK plus 1, that's orthogonal to all the previous columns. So we just keep growing this matrix QK by adding on columns. Each new column you can think of as kind of like a new direction to add on in a way. Okay. Now, I'm going to define QK to have these columns, Q1, Q2, and so forth, up to QK. And I'm going to define the first column, Q1, to be just B from AX equals B, the right-hand side, but I can't define it to be just B because these vectors are orthonormal, so that means they're orthogonal to each other, but what other property must they have if they're orthonormal?
The summation, the square summation of them must be 1.
Yeah, of their components. Yeah, they're a unit vector. Yeah. So I have to normalize B by dividing by its 2 norm. Okay, so we'll start off the matrix that way. So we use B as our first direction and go from there. Okay. Now, what I have to do is make sure that each residual, so what we want is our residual, what I'm going to call RK, which is B minus AXK, to be orthogonal to all previous residuals, RK minus 1, RK minus 2, etc., all the way down to R0. Okay. All right. But now I can fill in something for xk, because I prescribed a form for it. So I have rk is b, which is well, since q1 is defined this way, b is the same as its norm times q1, so a constant times u1, and then I have a, and then xk I can substitute in this form, qk, yk. Now I can go a little further. Q1 is the first column of the matrix QK, so I can write it as QKE1 because to get the first column of a matrix, if you multiply the matrix by E1, that extracts the first column for you. Okay. All right. Now, so what's interesting is, sorry, I'm just noticing a typo in the notes. I have QK, a matrix, it's bold for some reason. So matrix is not supposed to be bold. Okay. Now, one interesting observation here is the residual is a linear combination of columns of Q, well, this column of Q, and also vectors that you get by multiplying columns of Q by A. So, so what we can do is, since each residual is determined by multiplying columns of Q by A, what I'll do is I'm going to choose the columns of QK to be an orthonormal basis for what is called a Krylov subspace. Krylov subspace, which I'll define this way, fancy K, it's generated by the vector B, the matrix A, and I'm going to prescribe it has K vectors, so it's dimension K, and it's just the span, in other words, a set of all linear combinations of B, AB, A squared B, and so on, all the way up to A to the K minus 1 times B. So K vectors altogether. All right. So the effect of that is this residual RK is going to belong to Krylov subspace of dimension K plus 1. So it's like we have a hierarchy of Krylov subspaces, starting with dimension 1, just has B, and then we make an orthonormal basis from these two vectors, and then these three, and so on. We keep growing it from one iteration to the next, because since that covers taking columns of Q and multiplying them by A. So one way you can do that is, to grow the next Krylov subspace, all you got to do is if you just multiply what you have by A and then make it orthogonal, then you have your next Krylov subspace basis. Okay. So I want this residual. All right. So I want residual to be orthogonal to the range of QK. In other words, the span of all the columns. That way I can make sure that each residual is orthogonal to all previous residuals. Because previous residuals would come from previous Krylov subspaces. It's this way for all iterations. So another way of putting this is, I want QK transpose RK to be 0. So that is saying that RK is orthogonal to every column of QK. All right. So now all I got to do is take this equation right here that defines my residual and multiply both sides by QK transpose. And that's going to give me all these inner products. I need to require them to be 0. Okay. So I have QK transpose RK. So I'll fill in what RK is from before. So that's norm of B QK E1 minus A QK YK. Okay. Now, so once I carry this out, I'm going to have, well, 2 norm B, that's a constant, so that just gets pulled out. And then QK transpose QK Well, that's identity. So that's gone. So I have E1 minus QK transpose AQK, and I'll group all that together. And then I have YK. And I want that to be 0. Okay. Now, this matrix, I'm going to call that TK. That is K by K. And remember, A is symmetric positive definite. So TK is going to be also. Okay. So I want this to be 0. So my unknown vector, YK, has to satisfy this equation. TK YK is equal to norm of B E1. So now I just have this system of equations to solve. That's K by K. So my original system is N by N, and N can be very large. We're interested in those types of problems, but this can be much smaller. Whoops, that satisfies. Okay. So with each iteration, I just have to construct my xk as a linear combination of my columns of qk, and those coefficients in linear combination that satisfy this. So I could solve this system each iteration. Okay. Now, so I have like the beginnings of a method here. So I'll try to write out as semi-pseudocoded fashion what this is. So initially, I have Q1 equal to B normalized. Okay. And then I can define, say, well, okay. So then if I start a loop, okay. So my matrix Q1 would initially just have only the column Q1, little Q1 in it. So I can define TK to be QK transpose AQK. So during the first iteration, TK is going to be just a number. And then I can solve the system TK YK to be norm of B E1. So a very trivial equation the first time around, but the system's going to keep getting bigger and bigger. Then what I can do is I can define a vector, I'll call it Vk, to be A times by my last column of capital QK, but I'm not going to apply A to it. Then, let's see, what I need to do is orthogonalize Vk against capital QK. In other words, I need to make it orthogonal to all the columns. Then, I'm not running out of room here. So then what I need to do is define my new column of capital QK, QK plus 1, to be Vk normalized. And that's it. I can then resume the iteration. Now capital QK will have one column more, because this is going to be added onto it. So I can say QK plus 1 is equal to matrix QK, and then this is a new column. And then the iteration will proceed. So we have something anyway, and at least based on these considerations here, all the residuals are orthogonal. Okay. Now, I said this is the beginning of the method, and so there's some hurdles here. First of all, I have not described how to do this orthogonalizing. So we have this new vector, we need to make it orthogonal to all columns of capital QK. How do we do that? So I'm going to tackle that problem first. A second problem is, here we're solving a smaller system of size k by k. That's fine in the first iterations, but what if we need a lot of iterations? This system keeps growing and growing in size, so that eventually is going to become more and more expensive. So, so once we clear all these hurdles, then we can start seeing what the conjugate gradient looks like. Okay. Now, so first of all, these vectors, the Q's, the columns of capital QK, they are orthonormal. So we need an efficient way to generate these orthonormal vectors. So what we can say is that each of these vectors, fluid QK, is some polynomial of degree k minus 1 times b. So for instance, q1 is just a constant times b, so polynomial of degree 0, and so on. Also, so what we can say is, I can define an inner product of functions to be B transpose f of a, g of a times b. So it's rather unusual inner products of functions. So, so I want these polynomials to be orthonormal. So this would be B transpose Pi of A, Pj of A, B, to be equal to 1 if I is equal to j, and 0 otherwise. That is the Quadratic delta. Okay, so I try to find a sequence of orthonormal polynomials that will give me orthonormal vectors. So the vectors are orthonormal with respect to the traditional inner dot product. These polynomials are orthonormal with respect to this inner product. Okay. Now, orthonormal polynomials satisfy a three-term recurrence relation. So that's a well-known fact about all sequences of orthogonal polynomials. Okay. Where the alphas and betas are recursion coefficients, these are constants. And this relationship is true for j equal 1, 2, and 3, so on. And to make a recurrence relation make sense, so this is called a three-term recurrence relation, because each polynomial depends on the previous two. So there's 3 involved altogether at one time. So to make it make sense, even when j is equal to 1, I need to define p sub minus 1, that'll just be 0. And then p sub 0 is a constant, it's just 1 over the norm of b. Okay. In the notes, I made an assumption that norm of b is equal to 1, but for convenience and laziness, but I'm not doing that here. Okay. Now, the way that's obtained is using Gram-Schmidt orthogonalization. Like, for instance, like the monomial basis. Okay. Now, how do we get these coefficients, the betas and the alphas? The way we figure that out is by enforcing that these polynomials have to be orthogonal. So for instance, I can take the inner product with Pj. Let's see, is that one? No, inner product with Pj minus 1. So the inner product of this of Pj minus 1 is going to give you a left side of 0. Because the polynomials are orthogonal. On the, also Pj minus 1 is orthogonal to this term. So that's going to be gone. The only thing left is going to be this term. I'm going to have inner product of Pj minus 1 lambda Pj minus 1 minus alpha j is a constant, so that can be pulled out of the inner product. And I get Pj minus 1, Pj minus 1. But that is 1 because these polynomials are required to be orthonormal. So that gives me a formula for alpha j. Just by requiring orthogonality. Now, I can take a similar approach to obtain formulas for betas. So I can take the inner product with P. I have a different formula here in the notes, but okay. So inner product with, for instance, Pj, and I get beta j on the left side. On the right side, most things will be 0. The only thing that's going to be left is inner product of Pj with lambda Pj minus 1. Okay. Let's see. So at least we have ways of getting these recursion coefficients. Although a more efficient way, I won't go through all manipulations here, but I could find it to be the inner product of so beta j squared is the inner product of rj with itself, where rj is just the right side of a recurrence relation. So you think of the rj's as polynomials that are orthogonal but not orthonormal. They're not normalized. Once you normalize them, then you get the p's. Okay. So if I now this recurrence relation is applied to a generic independent variable lambda, but I can also apply it to the matrix A. So so I have beta j Pj of A is equal to A minus alpha j identity Pj minus 1 of A minus beta j minus 1 Pj minus 2 of A. And then what I can do is I can multiply both sides of this by vector B. And now, using my definition of vectors qk, I can say that beta j, this is qk plus 1, is equal to A minus alpha J identity Q, J plus 1. Qj minus beta J minus 1 Q J minus 1. So this shows how all the columns of capital QK are related to one another. So they satisfy free term recurrence also. Okay. And then, oh, my dang thermostat again. Okay. So this shows how I can build my Quetelet subspace basis by obtaining each vector from a previous two. And thus ensuring that they're orthonormal. But one thing that's also quite convenient is, from my recurrence relation, if I were to rearrange this, I have AQJ is equal to, so this term I leave here on one side, and then all of our terms go on the other side. So I'm going to have beta J minus 1 QJ minus 1 plus alpha J QJ plus beta J QJ plus 1. Now, if I were to write this relationship out, this is for generic J, but if I were to do it for all J up to a certain point, and put all these together, I have AQK is equal to QK times a tridiagonal matrix that has the alphas on the diagonal and betas above and below. And that comes from the constants that are multiplying all these vectors. And the reason why it's tridiagonal is because I have three terms here. Here I have QJ. Here I also have QJ. Thus it's a diagonal entries, the same index. Because these indices are one off, either less or greater than, it leads to the sub and super diagonal. So the subdiagonal actually comes from this term, and the super diagonal comes from this term. So just following the rules of matrix multiplication leads to this relationship. But there's one term I'm missing. So in the last because like when J is equal to little k, I'm going to have beta J Q K plus 1, and that's not included in here. So I have one more term, beta K Q K plus 1 EK transpose. In other words, this EK transpose, that's a row vector that has all zeros except for one in the last position. So it puts this in the last column. Now, let's suppose I take this equation and I multiply both sides on the left by QK transpose. So, I don't want to go to the next board yet. So, your notes will look more coherent at least. So then I get QK transpose AQK is equal to, well, QK transpose QK, that's identity. So this matrix remains, the alphas and the betas. And then this term qk, capital QK, is orthogonal to this, because this is the next vector in my orthonormal basis. So this term's not going to produce anything either. I only have that. But I gave this a name earlier. I called it TK over there. So now we know what TK is. We knew it's symmetric, but now we also know that it's tridiagonal. We didn't know that before. And it's tridiagonal because of the conveniences of orthogonal polynomials. Each one depends only on the previous two. Okay, so one nice thing about the sketchy algorithm I have over there is, okay, we're having to solve this system in each iteration, but it's a tridiagonal system, so at least it takes less time. But we still don't really want to be doing it. We don't really want to be solving the whole system of equations every iteration, even if it's a small one. But at least now we have a somewhat better defined algorithm in that we now have a way of generating these orthonormal vectors. So I can now, so you can think of this as version 0 of a better algorithm than steepest descent. Now I'm prepared to write down version 1, and I'll just have more details than this. Okay, so okay, so we'll start out with R0 to be just B. Define, now my Q vectors are numbered starting at 1, but for convenience I'll define Q0 to be 0 vector, just so other equations later on make sense. And my initial guess to the solution of Ax equals B, that will be 0. Alright, so now we start a loop. Okay, so first thing I need to do is I need to take my, actually, I'm going to start at k equal 1. Okay. Now, I'm going to define each beta to be my latest R vector normalized. Okay. And then, then I'll define my new Q vector to be my latest R vector divided by that norm. Alright, so just normalizing here. Okay. Now, I'll apply A to that latest vector. I did that before. And then I can compute alpha, okay, is shoot. Okay, this wasn't even in a note either. I need to explain where that came from, because that's the same alpha I had before. Alpha k is the inner product of pj minus 1 lambda pj minus 1 with this inner product of polynomials. However, that's defined to be pj minus 1 of A times B, dot product with A, pj minus 1 of A times B. But pj minus 1 of A times B, that's equal to, dang it, times alpha j here. Pj minus 1 of A times B, that is Qj. So that's Qj transpose AQJ. And that is Vj. So that's where this formula for alpha the alphas come from. So we start with orthogonal polynomials, but then we use those orthogonal polynomials to define orthonormal vectors. Okay. And then some vectors that we work with, because that's a lot easier. Now, I can define RK to be EK. And here's where I use the free term recurrence relation. So this is the same recurrence relation that I have over there in terms of the vectors, the little q's. So now this will be used up here to keep growing the orthonormal basis of the little q's. But in the meantime, I still have my system solved. I can say xk is, all right, so the norm of b times qk yk, where yk comes from solving this system of equations. Okay. Actually, one. I can check their other notes here. Yes. Okay.
For RK,
Yeah.
should that be beta PK?
Yep. Can't keep my letters straight today. This does not bode well. At least at the end of the day. Okay. All right. Okay, got it. All right, so now, and that's the end. So we're still solving the same system that's growing in size of each iteration, but now we have a systematic way of and efficiently computing the columns of capital K, or orthonormal basis. And it turns out, or what you can do is, using the equations that I had earlier for residual, that b minus axk can be shown to be minus beta k qk plus 1, and then times the last element of the vector yk. So notice I have no vector symbol here. That means it's a scalar. So it's just the last component of this vector. But each residual is the next multiple of the next orthonormal vector to orthonormal sequence. So that means that each residual is orthogonal to all the previous residuals. All right. Now, I'll bet that someone in this room, based on recent experience or other classes, can tell me what algorithm this is.
Branches.
Yes, it's a Lanczos algorithm.
Well, I have to know because my depend is so close. You know, if I don't answer this question, it means that something is wrong with me.
Yeah. So, well, you should be most familiar with it. Anyway, okay. The Lanczos algorithm isn't always used for solving systems. As it can serve other purposes too, like computing eigenvalues and eigenvectors of symmetric positive matrices, for instance. And I use it for evaluating integrals. But this tridiagonal matrix, TK, that we get, also known as a Jacobi matrix, plays an important role. Okay. Now, so now we have an improvement on steepest descent. That because now the main most expensive operation is right here. A matrix vector multiplication. Can't really do anything about that, but that's okay. We only have just this one per iteration, so that's good. And that's, it's an order n squared operation, or maybe even less if the matrix A is sparse. This we'd like to deal with though, because solving a system of equations. If we can avoid doing that at each iteration, that would be nice. Because also, what if a matrix is ill conditioned, for example? Also, we're trying to develop a non-stationary iterative method where each iterate is a previous iterate plus some multiple of a search direction. And we don't have that here. We don't have any obvious connection between this iterate and the previous one. So we'd like to have a method in that form, if we can. Now, so in order to do that, we're going to modify this method even further. And hopefully I can finish this before we're done. I don't know. Well, we'll see. Now, so let's return to the matrix TK. It is symmetric, positive, definite. It's also tridiagonal. Now, what can I do with a symmetric, positive, definite matrix? How can I factor it? We talked about this last time. What?
I was talking to myself.
What factorizations are available for symmetric, positive, definite matrix? Take a stab at it. I guess.
LVOT.
Yes, that's the one.
That G times G transpose?
Just Cholesky. Yeah. Yeah. So the one we need here is LDLT. So because we know TK is symmetric, positive, definite, it has this factorization. Also, because TK is tridiagonal, L has a lower bandwidth of only 1. So it has this structure. One's in the diagonal, and then these scalars directly underneath. And then DK, that's a diagonal matrix. So let's name these diagonal entries. So this is going to turn out to be very convenient for us. That has, we have this nice structure. Okay. Now, I'm going to make a definition here. Find this matrix PK tilde to be equal to QK LK inverse transpose. Now, we know it has an inverse because it's lower triangular and the diagonal entries are all 1. Okay. Now, so what this would mean is, if I look at my iterate xk, which is already known to be qk yk, but yk is defined to be, I should have a norm of b in here. Okay, forgot that. Yk is tk inverse, oops, forgot again. Tk inverse E1. But I can express tk inverse in terms of the LDLT factorization. So tk inverse is going to be lk inverse transpose dk inverse lk inverse times E1. Okay. So now, this gives me a way to express this iterate xk in an alternative form. So, all right, qk lk inverse transpose, that's pk tilde. And then the rest of this, I'm going to call this WK. That's a vector. Okay. And WK satisfies this system of equations. LK dk WK is equal to E1. All right. Now, so now I have this system of equations to solve, except this is going to be a lot nicer. And here's why. If I break down the structure of this, LK is the same as LK minus 1. So this is LK here. And then I have a 1 here in the diagonal entry. And then I have little LK minus 1 is the last entry here. Everything else is zeros here, here. And then capital DK, the block diagonal structure. 0, 0, DK. And then I have my vector WK minus 1 for previous iterates. I have a new component being added on, little WK there, and that is equal to E1. Well, E1 is E1 up here of a smaller dimension, and then it's 0 down here. So now I've broken down the system to a nice block structure. So what I can do now is break this down into really more like a system of 2 equations rather than just 1. So what I have is, okay, I can combine these into 1. So now I have LK minus 1 times DK minus 1 WK minus 1 plus 0 times the last element is equal to E1. So this system is exactly the same as this one, just index 1 less. Okay, so no surprises there. But then, for the rest of the equations, I have all this vector, times, okay, well, I need to form this vector to be able to better see what I'm doing. So this dk minus 1, wk minus 1, and the last component, I have little dk, wk. Okay, so now if I carry out the product of this last row with this column, what I get is LK minus 1, little dk minus 1, WK minus 1, okay, plus dk WK equals 0. So what that means is each new element of a vector WK comes straight from the last one. So it gives me an easy relationship between each iterate and the previous iterate. Okay. So another way of putting this is the vector WK is a vector WK minus 1 with a new element added at the bottom that satisfies this. So that's important because it means each iteration can build up a previous one in a straightforward way. We did not have that earlier with, oh my god, I forgot to move a computer. Alright, well I need to look at this anyway. This system right here, YK each yk has no clear relationship for previous yk. You can't build off it. What I was showing here, and now everyone watching at home, so um, Candace, Stephanie, and Vivian can see what I worked through right here. Sorry about that, but it's all in the notes. That now each vector wk in this form of my iterates each new iterate builds from a previous one in a straightforward way because we're using reusing coefficients in the linear combination. Because this vector indicates linear combination of coefficients of pk tilde. When we were taking linear combination of the columns of qk before, we weren't reusing coefficients necessarily. Now we know that we are. Okay.
Excuse me, the second equation, that shouldn't be large D, or am I wrong?
Oh, what happens is, oh wait, here?
Yes.
Well, the thing is, I'm taking this vector dot product with that.
That.
And L of that's 0 except for the last element.
Yes, then LK minus Y should be multiplied by large D.
Well, what I'm doing is I'm taking the last element of this.
Okay, got
But that's just a diagonal matrix times this vector.
Mhm.
Okay. All right. So what I have as a result is xk turns out to be equal to xk minus 1, which uses these linear, these coefficients for linear combination, plus wk times pk tilde, this vector that is the last column of a matrix, capital tilde capital PK. All right. Now, so now we have a form for a non-stationary iterative method. You can think of this as a search direction. Now we're going to normalize it more later, but so now by expressing solution in this form and taking advantage of the LDLT factorization, we have this. We no longer need to solve a tridiagonal system, at least. And at least we have an easy way to build from one coefficient from a previous coefficient, thanks to this nice LDLT structure that we have going here. Okay. There's something more that we have. Okay. In terms of how these columns relate to each other. Alright. So PK tilde transpose A PK tilde. If we take a closer look at that, well, PK tilde was defined to be QK LK inverse transpose. Okay. But now I take the transpose of this. Transpose of products and product of transposes in reverse order. So I have LK inverse QK transpose AQK LK inverse transpose. QK transpose AQK, that is TK. TK has an LDLT factorization. We'll fill that in. Well, these cancel out. And we're left with DK. So, the reason why this is important is if we look at this matrix on an element by element basis, so I take column I of this and column J of that, Pi tilde transpose A Pj tilde, well this whole thing is a diagonal matrix. So this is equal to di if I is equal to j, and 0 otherwise. Now, I wanted search directions before that were orthogonal, and that would mean like Pi transpose Pj is equal to 0 if I is not equal to j. I don't have that here. I almost have that. I have an A in the middle. So what we can say is these columns are A orthogonal, also known as A conjugate. So they're orthogonal with respect to a different dot product or inner product, what we normally do with vectors. Because normal dot product is like x transpose y, but now we have like x transpose ay. So it still means linear independence because A is symmetric positive definite. So you can still define an inner product with any symmetric positive definite matrix in the middle. So at least it gives us independent search directions if not orthogonal ones. And they're orthogonal in a certain sense. And because we're using different directions in each iteration, and we only have n directions total to use, this iteration is guaranteed to converge in n iterations. Now we like to do even better than that, converge to whatever tolerance and far fewer than that, but at least it gives a clear stopping point. It's not going to run on forever like steepest descent would. Okay. So, because we are using A conjugate search directions, and the search directions, they're not the steepest descent, but they're basically modifying the steepest descent direction, which is a minus gradient. That's why this approach I'm describing is the method of conjugate gradients. So that's where the name comes from. Now, from the relationship that we have between how P tilde was defined, so we have Pk tilde Lk transpose is equal to Qk. Let's exploit that as best we can. So Pk tilde has the vectors P1 tilde, P2 tilde, up to Pk tilde. Lk transpose is a upper bidiagonal matrix. So we have 1 to the diagonal, and then these scalars L1, L2, Lk minus 1 at the bottom because of a transpose. And then we have Qk on the right with all its columns. So what this means is if we carry out the matrix multiplication, and then we look at this column by column, we'll have a vector Qk on the right, or Qj, for whatever index j I choose. And then, on the left side, here I'm using this to combine columns. So what I get is Qj, for each column, Qj is equal to Pj plus L j minus 1 Pj minus 1. I can tell this here. So we have a simple relationship between the search directions and the residuals. Because remember, each residual is a multiple of Qj. And this is true for j greater than 1. And we also have P1 tilde equal Q1. All right, so that shows how the search directions are related to the residuals. Okay. So in fact, I could rearrange this. I could say that each search direction is equal to, it's defined as a linear combination of the latest residual and the previous search direction. I wrote that relationship down last time. So that's how we're modifying steepest descent. We're correcting it by adding on a multiple previous search direction to preserve all these properties and give steepest descent some memory. Okay. Yeah.
These P tailors and Q tailors have the same properties that P and Q had. For example, P was money.
Oh.
They still have those properties? Or these
Oh. Okay. Well, the P's were before. Those are actually all for normal polynomials. So you're thinking of other notes.
Yes. I mean, are these the same, or these two are two different things?
I think of them as at least slightly different.
Okay.
Yeah, because I've used different conventions in other sets of notes. Yeah. It's hard to stay consistent with these notes. Okay. All right. Now, what happens in actually formulating conjugate gradients? Okay, where did I leave off here? Okay. Oh. Well, trouble is I have 2 pages and 8 minutes. So I won't have time to go through all the manipulations here, but I'll do what I can and actually remember to remove the computer. Okay. All right. We just normalize things a little differently. That so I'm going to let pk no tilde be equal to the norm of rk times pk tilde. So I'm just renormalizing things. Okay. So the result of that is if I take okay. So now if I multiply the previous relationship by this is 2 normal bar j. Okay. Then, so from this, the scaling the previous relationship by this norm, I get pj without a tilde there. And then this is just rj, which from the equation I gave before actually is the residual from Lanchell's iteration. And then I'm going to move this to the other side and give a scaling constant a new name. I'll call it mu j. Okay. So we have some constant there, which, based on what I have above, is equal to minus Lj minus 1 normal bar j. But the thing is, we don't have to even use that. Oh, wait a minute. No, that's not entirely correct. And this term is matched with this one. And each pj is a multiple of the previous of the pj tilde, but I'm not going to use this to define this. I don't need to. What I can do instead is I can define this by enforcing a orthogonality. So what I'm going to do is I'm going to multiply both sides of this equation first by a, and then take the dot product with pj minus 1. Okay. Now, this helps me because the search directions are A orthogonal. Therefore, the left side, 0. And now I can just use that. So now I can solve for mu j. So mu j is equal to minus pj minus 1 transpose arj over pj minus 1 transpose a pj minus 1. Okay. So now that I know the search direction is supposed to be orthogonal, I can use that to define whatever constants I need. Okay. So what that means is I don't need the q's anymore. They're eliminated. I still have the residuals at each step, but and I'm developing my search directions using its recurrence relation, but qj is gone. All right, so now we'll just get the search directions from the residuals. Okay. Now. Okay. I may return to this on Thursday, but I want to skip to a more central part of the notes here. We have this relationship between each iterate and the previous iterate. Xk is xk minus 1 plus, we had a multiple of pk tilde before, but now we know that's a multiple of pk also. So we have some scaling factor there, which I'm labeling as nu k. I can obtain that in the same way that I obtained mu over there. Enforcing A orthogonality. So what I can do is, because I also have a similar relationship between the residuals. Rk plus 1 is equal to Rk minus nu k A pk. Because if I multiply both sides of this by A, and then subtract B from both sides, or actually subtract both sides from B, I get this relationship because Rk plus 1 is B minus A x k. That's how I'm defining these residuals. Okay, so this plus this relationship gives me that. You can try confirming that for yourself. So I can use this relationship to figure out what the nu k should be. So the residuals are supposed to be orthogonal, not orthogonal, just plain orthogonal. So what I can do is I can take the dot product of both sides with Rk. Rk transpose, Rk plus 1, which must equal 0, is equal to Rk transpose, Rk, minus nu k, Rk transpose A pk. So now, because the left side is supposed to be 0, I can solve for nu k. Alright, so I have my essential constants defined here and here that give me a way to get each search direction from previous information, and also each way to get each new iterate from a previous iterate. And the same constant that gives me each new iterate also gives me each new residual. So I almost have conjugate gradient in the form that I want it. The only thing that I don't, that's bad about this is here I have A times PK, A times the search direction. Here I also have A times the search direction. But I also have A times the residual. I'd rather not have that. I want to have, that requires 2 matrix vector multiplications per iteration. And we already know that this job can be done with only 1. So we need to try to sort that out. But I'm out of time for now. So actually I'm over time. So I will have to return to that on Thursday.